Hello everyone, welcome again to Modeling Methods in ME, and today we are going to shift gears from where we started the semester. Remember, we started the semester talking about field theory and the different aspects of field theory and their applications into mechanical engineering in particular. We talked about the different vector operators, such as the gradient, the divergency, the curl, the Laplace, and so on, as well as integral identities that will allow us to account for things like that pertain to conservation, for example, using Gauss's divergency theorem or Stokes' theorem. Now we are going to look at curvilinear coordinate system, and from that standpoint, we're going to try to explain and refer to these integral and vector operators in different frames of references, because sometimes it's important and very appropriate that we, especially us as engineers, try to frame things with respect to another reference. So everything that we've derived so far has been in the Cartesian coordinate system, but sometimes it becomes more beneficial and productive and efficient to frame our problems into, for example, cylindrical coordinate systems if we are trying to solve things in pipes, for example, or in spherical coordinate systems if we're trying to solve things like, for example, acoustic scattering, which is a spherical phenomenon, or electromagnetic scattering, which is also a spherical phenomenon, or, for example, some force fields such as gravitational fields, which are a spherical phenomenon in nature or by nature. So it is important that we kind of establish a kind of a framework to be able to negotiate and navigate between these different types of coordinate systems and understand what's at stake and what needs to be done in order to properly refer and reference a vector field and its operations in one reference frame to another reference frame. All right, so this is modeling methods in ME, and our topic today is curvilinear coordinates and transformations. All right, so when I mention two curvilinear coordinate systems, the one that I just mentioned, the cylindrical and the spherical, I do so because these are well-known curvilinear coordinate systems that have a large variety of applicability. But obviously curvilinear coordinates are not confined to just those two. In fact, there's an infinite number of possible curvilinear coordinate systems in three-dimensional space. There's only about 12 of them, or actually 12 of them, that are orthogonal in nature, where every one of the three axes is perpendicular to each other. One of them, obviously, the Cartesian coordinate system, x, y, z. The other one is a cylindrical coordinate system, r, theta, and z. And the other one is one other one is a spherical coordinate system, r, phi, and theta. There's another one called the parabolic coordinate system, the hyperbolic coordinate system. All these different coordinate systems that happen to be orthogonal as well, they have a different realm of applicability, as we'll note in this lecture and future ones. So let's start with nomenclature, and let's start by saying that we have been working in the Cartesian frame, where we've expressed our system as x, y, z, and each of the tangent vectors, or what we call the unit normal vectors, but they're in fact tangent. Let me use another color for that. So let's say this right here is what we call EX, and this vector right here is what we call EY, and this vector right here is what we call EZ. And these are vectors that are unit in length, and they are actually tangent to each of the axes, normal to the corresponding plane. So there's a way to go forward and a way to come backwards into the Cartesian coordinate to a generic coordinate system, which we'll call curvilinear. And curvilinear because the axis might not be straight, and generic because it might not be orthogonal. So we're going to call this axis U, this axis V, and we're going to call this axis, let's say, W. As a point of departure. That's not going to be the case ultimately, but that's what we're going to do. And you notice that the unit tangential vector here and the U direction is called EU, and the unit tangential vector here is called EV, and the unit tangential vector here is called EW. And those vectors might not actually be perpendicular to each other. Not only that, those vectors might actually change direction as you move in the direction of a particular axis. All right, so there exists, so we call the U, V, W the curvilinear system. Okay, and there exists a forward transformation that allows you to actually go from the Cartesian coordinate system to this new generic curvilinear coordinate system by some algebraic relationship of x, y, and z. So you can get U from x, y, and z potentially, V from x, y, and z, and W from x, y, and z. Likewise, there's a backward transformation which will end up being more important than the forward transformation, because it's where we can actually deduce most of the properties and characteristics of this curvilinear system. So we can actually use an algebraic relationship between U, V, and W to come back to x, an algebraic relationship between U, V, and W to come back to y, and an algebraic relationship between U, V, and W to come back to z. All right. So that's where we are. So let me give you a example so that we kind of position ourselves in this context. For instance, the cylindrical coordinates, where U is R, V is theta, and W is Z. These are the three coordinates of the cylindrical coordinate system. And what's going to happen is that we're going to go from the Cartesian system, again x, y, z, through a forward and possibly a backward transformation to a system. Let me write down C in this direction. And by the way, Z extends infinitely in the negative and positive direction. And then R is the coordinate perpendicular to Z. It can actually extend in all directions. So all of these are R at any value of Z. And then we have a tangential direction, which is also perpendicular to R and perpendicular to C, and that is the theta direction. So this is theta, and we call it the cylindrical system because as you extend this in the T direction, you'll always, or in the Z direction, you can always refer to the theta plane, or the theta axis, the tangential axis. So we refer to Z as the axial axis, or the axis, R as the radial dimension, and theta as the tangential dimension. All right. So the forward transformation have a relationship an algebraic relationship which allows us to transform into the r direction from x, y, and z, and that's simply x squared plus y squared square root. So we can find out what the radial dimension is from the Cartesian ones by this. Theta, which is the tangential direction in terms of x, y, and z, is simply the arctangent of y over x. Yz from xyz is simply z. You can see that the z-axis is actually common between the two systems. That's the only one that doesn't change. And the backward transformation you can either try to establish a system of three equations or three unknowns to get x in terms of r, theta, and z, y in terms of r, theta, and z in terms of r, theta, and z. Or in this case, since you're already familiar, I suppose, with the r, theta, z system, that is just simply r cosine theta. Y in the relation to r, theta, and z is r sine theta, and c in relation to r, theta, and z is just simply c. They're common. And if you plug this in here, you'll notice that you'll get identity. So this forward transformation, this backward transformation corresponds to this forward transformation. So let's define a few things. That will be relevant and important to defining generic curvilinear systems. The first one is tangent vectors to u, v, and w. So again, let's draw this again. The z-axis, y-axis, x-axis, and I'm going to draw the u-axis here, the v-axis here, and the w-axis here, and I'm going to draw a position vector from here to here, and I'm going to call it, as we usually call the position vector, r. So the tangent vectors, so vectors that are tangent to u, v, and w, expressed in terms of unit normal vectors or unit tangent vectors to the xyz plane or the xyz coordinate system, we're going to call them AU, and that's just simply the r du, and that would be the x du in the x direction plus dy du in the y direction plus dz du in the z direction. Okay, so this is the position vector r, which is simply x, y, z in each of the directions, and now these are the partials with respect to the direction u. How does it change with respect to the direction u in each of the directions? Likewise, AV will be the r dv, so that's dx dv in the x direction plus dy dv in the y direction plus dz dv in the z direction, and then finally a w, which is dr dw, which is dx dw in the x direction plus dy dw in the y direction plus dz dw in the z direction. Right? So given the backward transformation, we can find the coordinates of each one of these. The backward transformation is the algebraic relationship that exists between u, v, and w to form, to give you back x. So therefore you can technically differentiate x with respect to u, v, and w, or theta and c in this case. So let's go back to, for instance, and the cylindrical coordinates, the backward transformation is x is equal to r cosine of theta, y is r sine theta, while z is z. So let me express AR. So AU would be AR is the position vector with respect to the r coordinate, which is the x, the r, and the x direction, plus the y, the r, and the y direction, plus the z, the r, in the z direction. So that would be AR. So the x dr is equal to the cosine of theta in the x direction. The y dr would be the sine of theta in the y direction. And the z dr is 0 in the z direction. A theta is dr d theta, which is dx d theta in the x direction, plus dy d theta in the y direction, plus dz d theta in the z direction. So this unit, I'm sorry, it's not unit, this tangent vector a theta is, well, the x with respect to theta would be minus r sine theta in the x direction. Dy d theta would be r cosine theta in the y direction, and the z d theta would be 0 in the z direction. And finally, AZ, which is dr dz, again dx dz, and the x direction, plus dy dz, in the y direction, plus dz dz, in the z direction. Then this tangent vector in the z direction in reference to the x, y, z unit vectors is, well, this with respect to c would be 0 in the x direction, this with respect to c will be 0 in the y direction, and this with respect to c will simply be 1 in the z direction. There are the three tangent vectors in the cylindrical coordinate system, and then we can make them unit in length, and that's very simple. To take any vector, any direction, and express it in terms of unit magnitude, all we have to do is divide by its own length, its own magnitude. So we can unit tangent vectors. So we can say ER is equal to AR over the magnitude of AR. So we take this first vector here, take the magnitude of that vector, which is this one squared plus this one squared plus this one squared square root. So that would be the cosine squared plus the sine squared, which is 1. Square root of 1 is 1. So the length of these vectors is already 1. That means that this vector is already the unit tangent vector. The second one is a theta divided by the magnitude of a theta. So if we take the second vector here and take its magnitude, this one squared plus this one squared plus this one squared square root, we'll get r squared sine square theta, r squared cosine square theta, and 0. We can take the r squared as a common factor, and it will be r squared times sine square of theta plus cosine square of theta, which is 1. So it's the square root of r squared, which is simply r. So the magnitude of this vector is r. So when we divide that vector by r, we get minus sine of theta ex plus the cosine of theta ey plus 0. Easy. And the last one, you can see that the length of that vector is already 1. So AZ divided by the length of AZ won't change anything. It will still be 0, 0, plus 1. So that's the 3 vectors and the 3 unit tangent vectors in the cylindrical coordinate system expressed in terms of cylindrical coordinates and expressed in terms of the unit tangent vectors in the Cartesian coordinate system. Now, for bookkeeping purposes and generalization of what we're trying to do, we're going to switch notations. Switching notation. So instead of using x, y, z for the Cartesian coordinates, we're going to be using y's for Cartesian, and we're going to be using x's for curvilinear. What I mean by that is, so we're just going to index these letters. Rather than using different letters for the Cartesian coordinate system, namely x, y, and z, we're going to use y1, y2, y3 for the different axes. And instead of using u, v, w for the curvilinear coordinates, in general, we're just going to index x. So we're going to call it x1, x2, x3. This is going to lead to this tensor notation, where the index actually sweeps through the different dimensions in that particular system. So again, let's say we have this is the Cartesian coordinate system. It's no longer going to be x, y, and z. It's going to be y1, y2, and y3. And then we have the position vector, r, and it's going to reference x1, x2, and x3. Okay. Now, why would this be beneficial and useful? Well, that way we don't, if we need to increase the number of dimensions from 3 to something else for whatever purpose or application, we don't need to keep track of different letters. It's also easier to program, although whoever came up, or when they came up with this type of notation, they were not thinking of computer programming. But it's a lot easier to bookkeep things that are indexed than bookkeep things that have different names. You have to declare a variable for each one of them rather than declaring an array of variables. So this would be the forward transformation. Well, this will be the backward transformation. So you can see now that these expressions are more compact, where the index actually denotes the number of dimensions. So we have a set of 3 expressions for the backward transformation y. Remember, y is a Cartesian coordinate system, where y1 is a function of xk. K has three components, 1, 2, and 3 for dimension 1, dimension 2, and dimension 3 of the curvilinear coordinate system. Now, I mentioned that it's easier and actually more efficient to express these in terms of indicial notation, in terms of indices, because what happens when we have to increase the number of dimensions? Well, how is that even physical to increase the number of dimensions? Don't we always live in, for example, a 3-dimensional world? Well, it turns out that we don't. This is part of what's called a Riemannian geometry or non-Euclidean geometry, where we can actually curve things at will and express things in generic curvilinear fashion. And later on, this was taken by Einstein and his general relativity to express space and time into a single framework and into a single 4-dimensional framework. So rather than going through the hassle of adding time as an extra coordinate, he just called it a coordinate system x1, 2, 3, and 4. In fact, he didn't use 1, 2, 3, and 4. He started at 0, and he expressed the time as a 0th coordinate in the 4-dimensional coordinate system. So, and later on in fundamental physics, there are other theories that make use of these and add a lot more dimensions than just one time dimension to sort of formulate and frame their theories. All right, so let's talk about a property that should always be respected in any type of curvilinear transformation. These are invariants. The measure of length, surface, and volume are invariant between coordinate systems. Which means that, well, if you have a chord that measures 10 centimeters, that chord will measure 10 centimeters whether you express the function that describes that chord and the x, y, z, or y1, y2, y3 Cartesian coordinate system, or whether you express it in whatever curvilinear frame of reference. It really doesn't matter. All right, so let's start with the first one. Let's start looking at differential arc length, dl. So if the unit of length is invariant, we have to use that in order to express the calculation of an arc length. Would be through an integral. So the length of anything will be the integral over that chord dl, right? So we need to be able to express this dl in terms of the differential, in terms of the coordinate system, in terms of the generic or general curvilinear coordinate system. So let's start with the position vector again. That would be x, y, and z. And the differential of the position vector, dx, dy, dz. But keep in mind that we're no longer going to use x, y, and z. Now we're going to use y1, which is equivalent to x, y2, which is equivalent to y, and y3, which is equivalent to z. This is what we are going to use for the Cartesian coordinates. So the differential arc length square is the differential of the position vector dotted into the differential of the position vector. So dl square is dx times dx plus dy times dy plus dz times dz. Sorry. So basically take this differential of the position vector and square it. Or dot it into each other, I'm sorry. And then you'll get the scalar. So, and now expressing this new system, this will be dy1 dy1 plus dy2 dy2 plus dy3 dy3. And then if you recognize this is a summation of a product. So you can express this as a summation from I equal 1 to 3 of dyi dyi. Or you can just simply say, or dl square is dyi dyi. So we will omit the summation. It is implied. Anytime there's a repeated index in Einstein notation, repeated index or indices imply summation. over all dimensions of that index. In this case, I can take on the values 1, 2, 3. In the case of Einstein's general relativity, I can take on the values 0, 1, 2, and 3, 0 being the time dimension. Anyways, so if we express this R now in terms of the curvilinear coordinates, x1, x2, and x3, the position vector in terms of curvilinear coordinates, then we'll this is ultimately what we want. This is basically saying that the differential arc length in Cartesian coordinate system is dx squared, dy squared, dz squared. We already knew that. So the differential arc is the square root of all these. And then if we want to calculate the length of anything, we can just take a piece of the arc length and parameterize it, and then express each one of these square differentials in terms of the parameter c, for example, or L. But in the curvilinear coordinate system, well, we're going to do something similar, and then dr, the differential of the position vector, is dr with respect to xi dxi. Notice that these are repeated indices. Which in Einstein notation, again, it implies that there's a summation in front of it. So if you want to expand that, this would just be dr dx1 plus dr dx2 plus dr dx3 dx3. So by applying chain rule, we find that the differential of the position vector is dr in terms of each of its variables, x1, x2, and x3. All right. So if you recognize each of these terms right here, these are the tangent vectors, not the e's but the a's, not the unit ones but the full ones. So the differential of the position vector expressed in curvilinear coordinates is a1 times dx1 plus a2 times dx2 plus a3 times dx3, again, which is simply ai dxi. Again, the fact that there's two indices that are repeated, both are named I, means that there's an implied summation over all possible dimensions that I can take, 1, 2, and 3. So it will be a1 dx1, a2 dx2, a3 dx3, exactly as it is expressed here. Also, the fact that there's an I attached to a parameter like a implies that that parameter is a vector, right? So we don't have to write the arrow. Same thing for dx. dx is a vector, and we don't have to write the arrow. So dl squared, therefore, the differential arc length square, which is equal to dr dotted into dr, and in this case is ai dxi. And now I'm going to be careful not to use the same index for the second one. I'm going to use aj dxj. So these two are repeating, and therefore there's a summation implied between these two, and there's a summation implied between these two. So we're essentially multiplying these vector times itself, right? So dl square is ai aj times dxi dxj. Right there. So all we did is switch things around, and that actually works out. AIAJ is some sort of system that contains coefficients I, or contains index I and contains index j, right? So sort of like a square array of 3 by 3. That each of these elements of these array, a 3 by 3 array of parameters a times a, multiplying each of the coordinates, the x1, the x1, the x2, the x2, the x1, the x2, the x1, the x3, so on, all 9 possible combinations of these would actually make up the square of the differential arc length. These term here, or this array, we call Gij, is AI times AJ, and this has a very important name and meaning in all of Riemannian geometry. This is called a metric tensor. So it is in fact a tensor, is a square array from units from index I from 1 to 3 and index j from 1 to 3. So it's a 3 by 3 array that contains the metrics, or essentially the relationship between each of the coordinates in the curvilinear coordinate system that will make up the differential arc length. So dl square implies a double summation. So Gij dxi dxj, which is a metric tensor, the square of the differential arc length, implies, because of the 2 repeated index, I and j, implies the summation from I equal 1 to 3 times the summation from j equal 1 to 3 of Gij dxi dxj. Okay, that's it. These 2 summation signs are implied. So this is a double summation, right? So essentially dl square would be G11, or the first element of that tensor, times dx1 dx1 plus G12 dx1 dx2 plus G13 dx1 dx3 plus G21 dx2 dx1 plus G22 dx2 dx2 plus G23 dx2 dx3 plus G31 dx3 dx1 plus G32 dx3 dx2 plus G33 dx3 dx3. So the G tensor, the metric tensor, contains 9 elements. There are some properties of Gij, of the metric tensor. Number 1, Gij is equal to Gji. So it is symmetric. The metric tensor is always symmetric, regardless of what curvilinear system you're expressing. The parameter that relates how the relationship between the arc length to the arc length in Cartesian coordinates of 2 different coordinates is reversible. Okay, this tensor is symmetric. Furthermore, another important property of it, so it is always symmetric, no matter what. And another important property is that if coordinate 1 is perpendicular to coordinate 2 and it's perpendicular to coordinate 3, then Gij is equal to 0 for I different than j. So the off-diagonal components of this tensor are equal to 0. And that means that the system x1, x2, and x3 is orthogonal. So we can decipher whether a given curvilinear system is orthogonal by looking at its metric tensor and checking for the off-diagonal terms. If all the off-diagonal terms, all of them have to be 0, all of them are 0, then the system happens to be orthogonal. This is not a general property. A general property for all curvilinear systems is that this metric tensor is symmetric. This is a property that only applies to systems that are orthogonal, so we can decipher whether the system is orthogonal by checking this metric tensor and making sure that, by checking whether the metric tensor is diagonal or not. So therefore, for orthogonal systems like cylindrical and spherical and others, the differential arc length square, which is Gij times dxi dxj, simply boils down to this Gii, because the diagonal elements of G are the only ones that survive. So we can express dl as simply the square root of Gii, each of the members ii. And by the way, these repeated indices here do not imply summation. In this particular case, I'm not implying summation. Repeated indices here do not imply summation. What I'm trying to denote is that if you expand dl square, all of these ones will disappear, all the off diagonals will disappear, right? Because G12 is 0, G13 is 0, G21 is 0, G23 is 0, G31 and G32 are 0. So the only ones that will remain are these. So it will simply be G11 dx1 dx1, G22 dx2 dx2, G33 dx3 dx3. And then we can just simply take the square root of that and express dl as this will be the ith component of this tensor. Of this differential arc length will be the square root of Gii times the differential of the ith coordinate, where the square root is called hi. So hi is the square root of the ith diagonal term, and we call this one the scale factor. The scale factor. So dli is equal to hi dxi. I'm sorry, this is just dl, not dli. Just dl, the differential arc length, is hi times dxi. Well, the ith one, that was correct. All right, so scale factors. Hi only exist for orthogonal systems. They only have a meaning or relevance for orthogonal systems. So taking the square root of each of the diagonal elements of the metric tensor and calling them scale factors only has relevance when the off-diagonal members are 0. And that only is the case for orthogonal systems. All right. So, how do we go about determining the elements of this metric tensor? Determining elements of the metric tensor Gij from backward transformation. Right? So given yk, which is yk of x1, x2, x3. So if I have the backward transformation, or the algebraic relationship from the curvilinear coordinates to the Cartesian coordinates, we can calculate dyk as dyk dxi dxi. That repeated index implies a summation, so I'm going to write it out completely. This will be dyk dx1 dx1 plus dyk dx2 dx2 plus dyk with respect to the x3 times the x3. So we can express the L square, the square of the differential arc length, as dyk times dyk, as a summation of this one times this one, because that gives us exactly what we had expressed before. So dyk dxi dyk dxj times dxi dxj. So if we compare these to the fact that dl square can be expressed as gij times dxi dxj, we notice that the elements of the metric tensor are simply found by differentiating the backward transformation with respect to xi and with respect to xj, where in here implied summation over k, because k is a repeated index in this operation, so it is implied that this will add together. So for example, to find the first element of the metric tensor g11, we will take the dy1 with respect to the x1, so differentiate dy1 with respect to x1, differentiate dy1 with respect to the x1, plus dy2 dx2, dy2 dx, this is 1, this is still 1, dx1, plus dy3 dx1 times dy3 dx1. So notice that the summation that is implied is over k. Okay, so we'll take the first coordinate of the Cartesian system, backward transformation, differentiate with respect to x1, with respect to the second coordinate with respect to x1, the third coordinate with respect to x1, square all of them, and that will provide you the first element of the metric tensor. Likewise, for example, we can do the second element, element 1, 2 of the metric tensor, the second element to the right on the first row. This will be dy1 dx1 dy1 dx2 plus dy2 dx1 dy2 dx2 plus dy3 dx1 dy3 dx2. So take all the, and then that will actually provide you all the elements of the metric tensor all the way to G33, providing you all 9 components. But remember, the metric tensor is always symmetric. So if you calculate G12, you don't need to calculate G21. This will be equivalent to it, will be perfectly equivalent to that one. All right. So let's look at the differential areas. So that's when it comes to differential arc length. We'll do some examples on a future lecture of how to implement this in integrals, for example. So let's look at 2 differential areas or surfaces, ds. So we look at the Cartesian coordinate system. Which is again y1, y2, y3. We can take a little bit of x and call it dx. We can take a little bit of y and call it dy. And we can take a little bit of z and call it dz. So if we want to know, for example, what is the differential surface, the differential area on the xy plane, that will be that. This little shaded area here is the differential of surface perpendicular to the z-axis, and that is exactly, that square is exactly of the size dx dy. Well, if we want to do this on the ZY plane, for example, this right here is a differential surface perpendicular to the x-axis, and that's dy dz. And if we want to do this here, that little square here is the differential of surface, let's see where I write this, perpendicular to the y-axis, which is dx dz. All right, now the counterpart to this, again, we're going to go forward or backwards to this one, and let's say that, again, for ease of and to kind of avoid confusion, I'm going to go back to UVW. So this is U, V, and let's say W goes like this. Again, and when we formulate this, we're going to use the index notation. And let's say that this is a little bit of, I'll use the red, this is a little bit of du, this is a little bit of u, du, this is a little bit of v, dv, and I'm going to have to go like this to express this surface here that is perpendicular to w, and this differential of surface perpendicular to w is a Jacobian perpendicular to w times du dv. So the area of that region is not directly du times dv because it's a curved region. It's not a perfect rectangle, and therefore we have to use this conversion factor called Jacobian, which we've already used before. Likewise, when we have dw here, and I can express these or project these in this curve system, that would lead to this area here, which is not a perfect rectangle, and therefore ds that's perpendicular to u is a Jacobian that's perpendicular to u, dw dv. And finally, this one here, when I project it on this plane uw, and I project this on the plane uw, that will lead to this area here, which is the surface perpendicular to v, which is a Jacobian of v times du dw. Okay, so that's the meaning of the Jacobian. It's just essentially a scale or a conversion factor that will turn your area in terms, equivalent terms of the two components that make up that area. So the ith differential surface, and when I say the ith differential surface, is a differential surface perpendicular on the plane that is perpendicular to the first axis, the second axis, or the third axis. For one will be the one that is perpendicular to u, so this one, this will be 2, and this will be 3, is equal to the tangential vector aj times, or crossed into the tangential vector ak, dxj dxk, where this, as you can see, is the Jacobian. So these magnitude right here of the cross product of the tangential vectors that are opposite or perpendicular to the ith dimension. So if the ith dimension is u, the first one, then these will be the two tangential vectors that are tangent to v and tangent to w. We cross product them and multiplying times dv dw, giving rise to this one. So we use the identity in order to resolve this. We use the identity that says that vector A cross into vector B dotted into vector C cross into vector D should be equal to A dotted into C, B dotted into C, minus A dotted into D, B dotted into C. So it's just a vector identity. So we can express the magnitude of AJ cross into AK as the square root of AJ cross AK dotted into AJ cross AK. That's how we calculate the magnitude of the cross product between two vectors. So it will just be that vector times itself, that cross product times itself, square root of that. And then we'll use this identity here and then say AJ cross AK, magnitude of that is equal to the square root of AJ, AJ, AK, AK, minus AJ, AK, AJ, AK. Right? So, the Jacobian of direction I, which is this one here, is equal to AJ cross AK, is equal to the square root of GJJ GKK minus GJK square. So this is a Jacobian of the surface transformation, which simply implies that the ith differential surface is the ith Jacobian times the other two coordinates, J and K. All right. Again, so if you want to calculate this differential surface in the first dimension, the first direction that's perpendicular, the surface that is perpendicular to the first dimension, you calculate the Jacobian that is perpendicular to that dimension times dimension 2, dimension 3. Likewise, if you want to calculate the surface differential that is perpendicular to the second dimension, dimension 2, you'll need to calculate the Jacobian of that dimension 2 times dx1, dx3. So these J and K here are what I is not. There's no summation here, there's no repeated indices. This is a Jacobian of the transformation. All right. So where Ji is the Jacobian of the surface differential of the ith surface differential. So ds I is simply the square root of gjj gkk minus gjk squared times dxj dxk. These right here, again, is the Jacobian I. Now notice that if the system x1, x2, x3 is orthogonal, then gjk is equal to 0 for j different than k. So dsi will be equal to the square root of gjj gkk dkk, dxj, dxk. So dsi is equal to, by definition, h is the square root of these. So this will be hj squared, hk squared, dxj, dxk. So the differential surface and perpendicular to the ith axis or dimension is aj, hk, dxj, dxk. This is only for orthogonal systems. All right. So let's continue. With the third kind. The third invariant is the volume. So we should be able to calculate the differential volume in curvilinear coordinates. And the differential volume is essentially the multiplication of the three tangent vectors, a1, a2, and a3, which make up a curved parallelogram, or I'm sorry, parallelopipe. Right? So the volume of that parallelopipe is the differential volume. The volume of this parallelopipe, remember, if you have three vectors that define a three-dimensional object, is a1 dotted into a2 cross a3. dx1, dx2, dx3. Okay. So this will be 1 in Cartesian coordinates, because the differential volume in Cartesian coordinates is dx, dy, dz directly. So the differential volume, if we do the algebra here, this will be the determinant, this whole thing here is the determinant of gij. So this is the square root of the determinant of gij of the metric tensor, dx1, dx2, dx3. This right here is the Jacobian of the volume transformation, Jacobian of the volume transformation, and so therefore the differential of volume is the Jacobian, not the ith or the first, second, or third Jacobian. There's a single Jacobian in three-dimensional transformation for the volume. And it goes like that. So how to calculate that Jacobian? Again, is the square root of the determinant of the metric tensor. And to calculate the Jacobian, the determinant of the metric tensor, remember this tensor is G11, G12, G13, G21, G22, G23, G31, G32, G33, and you might have different ways of calculating the determinant of a matrix. You can augment this vertically. I do it horizontally. I repeat the first two columns. G12, G22, and G32. And then I take the diagonals and add them up. The product of the diagonals and add them up, and then I subtract the product of the counter diagonals. Okay, same way we did cross product. This is how we calculate the determinant of a system, the determinant of these tensor, which is a matrix. Now, if system x1, x2, x3 is orthogonal, then Gij is equal to 0 for I different than j. So all these things here, G12, G13, G21, G23, G31, G32 will be 0. So it's this one, this one, this one, and this one. So the only ones that are non-zero are G11, G22, and G33. G11 and G22. So as you can see, the only multiplication that is non-zero is the forward of the first diagonal. The forward multiplication of the first diagonal. So the determinant for these cases, the determinant of Gij is simply G11, G22, G33. All the other ones go to 0. And therefore, this is equal to H1 square, H2 square, H3 square. So therefore, the differential of volume, the Jacobian, is equal to the square root of the determinant of Gij is equal to H1, H2, H3. So the differential of volume will be H1, H2, H3, dx1, dx2, dx3. And that's only true when the system is orthogonal. Only for orthogonal systems. We just use the metric tensors, the scale factors of the metric tensor and the transformation. Okay, so this is all I wanted to cover for today. This is an introduction to curvilinear coordinates, and we'll continue talking about how we can use this in the context of expressing the differential surfaces, differential volumes, and calculating integrals for relevant physical quantities, and also for the application of the vector operators such as the curl, the gradient, the divergency, and the Laplace, and so on and so forth. How would these vector operators be calculated, or vector operations be done in curvilinear coordinates? So thank you for your attention, and I'll see you next time.